Okay, continuing with this segment, our next speaker will be Armando Solar-Lezama. He is a distinguished professor at the Schwarzman College of Computing and also the Chief Operating Officer of the Computer Science and AI Lab, CSAIL, at MIT. Armando is going to speak to you about how AI is transforming software engineering.
Thank you. Thanks a lot. Very glad to be here. And in my research lab, and generally myself, we have been working for about 20 years now on this problem of how to bring more automation into software construction, how to leverage computing power to help people deal with tricky problems that arise when you're writing software. And I have to say, it's been quite a ride. When we started working in this area, the dominant question was, why are you working on this? This is never going to work. It's too hard. You need too much cleverness to write software. How is a machine going to help you? And suddenly, about 3 years ago, it switched very abruptly to, why are you working on this? This is a solved problem. There's already all these companies doing this. There is really no need to be doing this in academia. And it certainly has been quite a change. The very first paper we published in this topic, trying to get machines to help us write programs, a running example was, well, what if you want to drop every third bit of a stream of bits, which is, not the most ambitious of targets, but at least it worked, to today where people are actually seriously wondering, do we actually need to learn how to program? Does anybody need to learn how to program? Are we just about to make programmers obsolete, right? And we have this enormous gamut of production quality, fully deployed tools, and widespread use across industry. And it raises the question, so what is there left to do for academic research in this space? So this is a question that we've been fielding a lot in the last few years. And as it happens, just last week we released a report on the challenges and paths towards AI and software engineering. Try to give a summary about what are some of these open problems and what are some of these directions where current tools and current models still have problems. Why do you still need humans helping you write software? If you're interested, definitely a lot more detail there than in the 18-minute talk. But very broadly speaking, what are some of these open challenges? One really important one comes with out-of-distribution domains. What does that mean? Programming that doesn't look like the bulk of code that you can find in GitHub or out on the internet in general, right? Turns out everybody's code looks different, especially when you go inside companies that, as a rule, tend not to like to open source all the code they're writing. Oftentimes you end up with code that looks very different from the code that these models have been trained on. Program understanding, especially at scale, turns out to be quite a challenge. These models have become quite good at reasoning about code locally. And in fact, just 2 years ago, we released a benchmark showing that models were really not very good at reasoning about the behavior even of small fragments of code. And basically, it took a few more months for industry to catch up and actually essentially make this benchmark obsolete. But when it comes to reasoning about software at scale, that is still very much an open problem. Similarly, along that vein is this question of software design, right? Software is often designed with a wide range of goals, not just does it produce a right answer, but keeping in mind how you expect the code to evolve, possibly over decades into the future. And good software design is something that is really critical for good software engineering. It's something that is not specifically one of the goals for many of these tools. Similarly, when it comes to reusing code, there's a very basic mode of reuse where you have a function that does X, and somewhere else you need to do X, and the model tells you, yep, here's the function that does X. That's the simple case of reuse. But the real sophisticated case of reuse, the kind of reuse that you would expect from a skilled programmer, is the kind of reuse where you know that this new functionality that you try to implement can be assembled by taking this little bit of code here that was actually written for a completely different purpose, and this other little bit of code over there that was written for a completely different purpose, and that if you take this routine over here and you generalize it in just the right way, then you can bring all of those together and get your new functionality writing very little code, right? That's the kind of sophisticated reuse and sophisticated reasoning that is really today still beyond the scope of many of these tools. And the big one, and really the crucial one, is the specification challenge. How in the world do you actually tell the machine what it is that you're trying to do? What is this software supposed to do? And it is a little bit of common knowledge in the broader community that everything changed with the advent of LLMs. There is very clearly a before and after in the world of program synthesis and machine learning for software engineering, right when GPT-3 came out, and it became very clear that this was going to be a very powerful technology for working with code. But there's actually a lot of really compelling ideas that come from the research community, even before then, that still have a lot of relevance in this period. For example, back in 2017, we were actually working on this problem of how do you deal with code that has complex functionality where it might actually be difficult to describe exactly what you want it to do. Right? And today we live in a world where there's lots of code out there, lots of code that is ready for you to reuse it so that you can implement very rich functionality without actually having to write a lot of code. And this is great until you actually try to find this code, and then until you actually try to go and figure out how to reuse it. And when you actually realize that it kind of almost does what you want, but not really. And when you're dealing with relatively complicated functionality that can be hard to describe, today we can use natural language, but even natural language is not often sufficient to convey what we want. As a simple example, we used the case where we had a code editor, and this code editor had this plugin system that allowed you to do very simple, with very little extra code, implement things like syntax highlighting for new languages, new programming languages that you created, right? Very powerful framework, very powerful functionality until you actually try to reuse it. And so what we found was that, well, something as simple as I want to reuse the syntax highlighting functionality requires you to know that there's something called the rule-based scanner that you have to extend with your own scanner, but then you have to go to something called the source viewer configuration and override it with your own source viewer configuration that internally has to instantiate something called a presentation reconciler. There's actually something called a damage repairer. And suddenly you're wondering, like, what do these things have to do with syntax highlighting, right? It turns out that the whole framework has its own internal language and its own internal logic. And once you understand the logic, everything makes perfect sense. For example, in this case, the editor has this view of the world where there's a very nice data structure that reflects the state of the code. Every time you type new code, you're damaging the relationship between the view and the data structure. So you have to repair that damage to re-highlight things. Oh, OK, that makes sense. If you didn't know that before, how would you know that? How would you know what to search? How would you know what the right keywords are? How would you know what the right classes are? And it goes back to this problem of, yes, all the code is there. How do you find it, right? And LLMs are supposed to be the solution to this. You can go and describe what it is that you want to do, And out comes a very nice tutorial together with all the code, together with all the information that you need about how to do this. Sort of, because it's a lot of code, and very quickly you run out of buffer space, and it cuts off in the middle. But even more problematic, you still have to have a very specific prompt describing very precisely what you want, using the right class names. And here we're talking about a very well-documented API. This was a framework that lots of people used. There were blog posts. There were tutorials. It's an ideal case scenario for this kind of tool, right? What happens when you have to do the same thing, but for your internal company API that suddenly doesn't have all of these resources? Turns out API versions turn out also to be a huge problem for this. If the API has gone through 5 different versions, as most widely used APIs have, then suddenly you're going to get some mishmash of pieces that work with one version and pieces that work with another version. And this actually turns out to be quite problematic. But more importantly, there is this high-level problem of how do you tell the system what it is that you want to do if you don't even know what is the internal language that it uses in order to do this? So one of the ideas that we actually experimented with was allowing you to just take another system that was built using this framework and just start working with it. And at some point, you get to the functionality that you like, and you press a button that says, hey, I'm about to show you something. I'm about to show you the thing that I want. And you can go and exercise this functionality and then press another button and say, there. That thing that just happened, that thing you just saw, that's what I want you to figure out and tell me what to do, right? And that turns out it requires this very different way of interacting with the system, right? For those kind of situations where using just natural language is not enough. You really want to be able to give those live demonstrations. You really want to be able to show, look, the functionality that I want is like this one, but in this other context. But we're still at a very early stage in terms of being able to rely on these richer forms of feedback. And in fact, one of the things that becomes really essential to deal with that kind of a problem is having multimodal support through our language models. We're starting to see some of that in the frontier models today, but one of the problems that you run into is that there's not a lot of really high-quality data, especially when you go out towards the long tail of lesser used frameworks, matching the actual code with the actual behavior, right? And this is an example, for example, from a project that we just completed. This was really led by my colleague Wojciech Matusek and his student Beichen Lee. But the idea of this project was that we wanted to target the kind of texture generation infrastructure that is used for things like video games, right? Where essentially what you have is this little program that describes how to turn random noise into a nice texture that you can use to wrap your shapes in a video game, right? So it turns out there are widely used tools that designers can use to design these kind of textures. And on top of these tools, there's also Python APIs. So as soon as there's a Python API, you know that this is something where LLMs can help you. But what we really want is the following. We want to have a system where you can take a picture, let's say, of the carpet down here. And from that picture, you want to feed it to your language model and get out the code that when you run it is going to give you the equivalent texture. And oftentimes, right on the first try, you're not going to get exactly the same texture. You're going to have to do a little bit of local optimization in order to get really the right texture. But this is within the capabilities of modern LLMs, except for the fact that even though they've seen some of this Python code, they haven't seen enough of it to really understand how it works. And in particular, they haven't seen enough data matching the code with the actual behavior that you want, right? And this is where you really need to actually do some data augmentation. We actually had a pretty sophisticated pipeline to generate about 500,000 programs, such that every one of these programs could be fed through a renderer to teach the model about the relationship between when the code looks like this is the kind of texture that you get out. When you do that, you can actually get some pretty nice behaving system, right? These are some examples from some textures written in Blender comparing the input image with the image generated by the code produced by our system compared to a bunch of different baselines, right? And you can see that certainly most of the baselines, even sophisticated frontier models just don't do a very good job. Again, because they haven't really seen that relationship between the code and the behavior of that code, right? Here's a few more examples from textures produced by a different framework. Here's actually some examples directly from pictures, right? Actual pictures taken from a texture and what the model is able to produce, right? So on the one hand, this shows that it is possible to bridge this gap between these different modalities of interaction and code, and that fine-tuning a model that does this is within the reach of an academic lab like ours, right? On the other hand, it also highlights some of the limitations of just business as usual. So where do we see things going forward? On the one hand, I think programming tools will become more and more essential, right? The days where you could be competitive as a programmer just writing code in VI with absolutely no tool support beyond your compiler or interpreter, I think might be reaching their limit. On the other hand, there is still, and we believe for a very long time, going to be a very crucial role for human expertise, particularly the flexibility that humans can bring to the table in terms of very quickly being able to learn new things is actually going to be quite important, right? And AI tools for coding can truly be enablers of creativity, right? Allowing you to write code that otherwise would have been just too difficult to write. But I think there is care that has to be taken in terms of protecting the health of the software ecosystem. What does that mean? Well, if you have a tool where the tool works way better if you're using the old version of the framework for which there's hundreds of blog posts and hundreds of tutorials compared to the new version of the framework that just came out, that suddenly introduces a lot of inertia into the system, right? And if you can't nurture the ecosystem for those tutorials and those help forums to keep up to date with the new tools and the new frameworks, then I think there is some risk going into the future. And finally, I think we're going to start facing some important questions around this question of technical debt, right? We have these tools that we can use to dramatically improve our productivity and help us produce code that is much better structured, that is much more maintainable, that is freer from bugs. Or we can use it to build lots and lots of really, really bad code very, very cheaply and very, very quickly, right? And which one is it going to be? Both of those are possibilities, but I have to say I much rather live in the world where we pick option 1 as opposed to option 2. And so with that, I would like to now take some questions. Thank you. So this is a really good question, right? What role will software engineers play in an industry where AI is increasingly generating code, and how can they adapt to maintain their impact, right? So I think there's many different answers to this question depending on what kind of code you are talking about, right? So first of all, there's a kind of sort of frontier code that is difficult, challenging to write, that really requires all your creativity and brain power, that looks really different from all the code out there on the internet. I don't think we're going to be writing that code entirely by hand, but I think the development of that code is now going to involve a lot of figuring out how to set up the problem, figuring out how to orchestrate all the compute power to really focus it on how to solve that one problem, right? Today, we see these very impressive results of tools solving, competition-level programming tasks. What we don't see is the enormous amount of effort and investment that went into actually setting up the tools and targeting it towards that particular kind of programming. I think there's going to be a style of programming that is really more about orchestrating the tools and setting up the thing so that you can now let your cluster run for a day and have some confidence that after a day or after a week of running, you will actually get a piece of code that does what you want. Now, arguably, most people today are not writing that kind of code. And in fact, people talk about what's going to happen when we have this revolution in programmer productivity. We already had not just one, but multiple revolutions in programmer productivity. One of the most recent ones happened when we moved to managed languages, which made it possible to actually not have to write lots of complicated algorithms all the time, right? Most algorithms get written once, get put into the library, and now it's just a matter of knowing how to call the right library and knowing how to use it. So writing these very, very unique algorithms has already for many years been a bit of a very high-end but somewhat minority pursuit. When it comes to the broader volume of code, a lot of that is really about figuring out, what do we want to build? What is this program supposed to do? And how do we navigate the trade-offs between performance and cost and usability? And how do we adjudicate all of these conflicts between what this customer wants and what that customer wants? And programming is a way to settle those questions with very, very high precision, right? To say, this is what the solution is going to be. That's not going to go away, right? We still have to figure out actually what it is that we want to build. What is it that this service is supposed to do? What is the service? How is the service supposed to react when this particular crazy situation happens? So programming is going to be very, very different, but a lot of those fundamental questions around system design are still very much going to be there.